So since there's no questions on the homework, we're going to go on and jump into today's lesson. Now, yesterday we talked about parent functions and kind of seeing how did they move? What were the transformations? Was it up, down, left, right, vertical stretch, vertical shrink, or reflection? And kind of seeing, okay, this is the function, this is what happened from the parent to get to it. Today, we're going to be given functions and applying those transformations to them. So we're going to actually be moving the functions up, down, left, right, stretch, shrink, and reflections to it. Now, we didn't look too much at reflections across the y-axis yesterday. We will be looking at them today and applying them. Now, the first one we're looking at is this here. Now, luckily, you don't have to write all that down. It was already provided to you in the notes. But the big thing here is if it's a horizontal translation to the left or right, we say that it is, let's get a highlighter. Y is equal to f of x minus h, where h is the value of that movement to the left or right. So whenever we take a function y equals f of x, we can use this here to move it to the left or right. Now, if that doesn't make a whole lot of sense right now, that's fine. A lot of what we do throughout the year, when I give you these core concepts or the theorems or whatnot, don't make a whole lot of sense in the mathematical vernacular. It's confusing. And I will give this little nugget to you, a lot of proofs and a lot of theorems in the group of mathematicians who are pure mathematics. We'll write it for the pure sake of it being so confusing you won't even touch it. Mathematica Penticula, I'm butchering it, it is Latin. Newton wrote that. And he wrote it in such a confusing way for the pure purpose that no one could say he was wrong. Because if no one else can understand it, no one else can critique me on it. It's one way to do things. But if this isn't confusing, that's fine. When we start getting into the examples, it'll start making more sense. If it still doesn't, ask questions. Okay? Now, vertical translation, we'll be using this here, y equals f of x plus k. And if you remember to yesterday when we had the general examples, the plus k on the outside did move it up or down. The k or h value inside the parentheses moved it left and right. And that's similar to what we have here. I'm going to write it up here on the whiteboard. So it's a little bit easier to look back on as we're going through this here. So any questions on this here before we start these here? Okay. And really what we're going to be doing is moving these functions accordingly. So our first one here, let f of x equal 2x plus 1. Okay. Now the first thing we want to do is write a function g whose graph is a translation 3 units down of the graph of f. So when we say function g, we're talking about g of x. And the main reason we use g of x, h of x, q of x, z of x is so that we can differentiate between the two functions. So if I'm talking about or referencing a function g of x, we know that most likely it's not going to be 2x plus 1 because that is f of x. It's just a different way to name the function. So we can look at more than one at the same time without getting confused. Now this function here is a translation 3 units down. Would this be horizontal or vertical? Vertical, because up and down is vertical. So our vertical general statement was f of x plus k, where k is the amount of movement that we're doing up or down. So how far are we moving it? Down 3. So the value of k would be 3. We can technically put plus what? What would the sign with 3 be? Positive or negative? Negative. If we're going down, it's negative. So we could say plus -3, or we can just say -3. Questions on anything so far? Okay. So what is f of x? 2x plus 1. Let's replace it. Now, is there anything in front of the parentheses that we have for 2x plus 1? Is there a number in front of it, a negative sign, anything like that? No. So we can just drop those parentheses and just have 2x plus 1 minus 3. Now what can we do? Combine like terms, yes. 1 minus 3 is -2. So our new function is 2x minus 2. We have translated the function down 3. That's it. That's all we have to do. Questions? Any questions on this here? Feel good with this here so far? Okay. You don't have to rewrite that. I'm just rewriting it so I can keep the function there. Is y'all's, you can still see it on your paper. Mine's way up high. I can't see it anymore on the screen. Okay, let's look at this one here. Write a function h whose graph is a translation 2 units to the left of the graph of f. So we'll say h of x is equal to, well, left or right is horizontal. And our one for horizontal is f of x minus h. So how is it moving? 2 units to the left. So we'll need a 2. Because it would be -2. And you're right in saying plus, because a negative and a negative would make a positive. So if you want to go on and change that to plus, that's perfectly fine. So really we're saying, I'm just going to write it below it. If you went on and changed it to a plus sign, that's fine. If you know that most likely looking back, that'll get you mixed up on what happened, go on and write the second one. Okay? Any questions on how we got to this point here? So now we have what? F of x plus 2. F of x is equal to 2x plus 1, yes? Well, I can't just replace it because I don't have f of x anymore. I have what? F of x plus, what did we do? I replaced x with x plus 2, yes? So over here, I need to replace every x, so this one here with what? X plus 2. And that's what we're going to do. So I'm going to have 2. Well, it was x, it's now x plus 2 plus 1. Now we're not quite done yet because we have that 2 times a set of parentheses. We can simplify that. If we can, we're going to. And the way we can simplify it is by distributing the 2. We can multiply through by 2. Well, 2 times x is 2 times 2 is 4 plus 1. And that is it.
How'd you do this for the target? -2.
Because we're moving to the left. And left is always, because right is positive, left is negative. Because if we think of a number line, the positive numbers are on the right, the negative numbers are on the left. Any other questions on this here? Do you feel good with this here? Up, down, left, right? Okay. Let's look at some more. We are going to be doing part B. I would have to scrunch everything and skip steps to fit it in that gap. So I'm going to erase it for now. It will come back later. But we're going to look at A first. Write a function g whose graph is a translation 5 units up of the graph of f. So g of x is equal to our f of x plus k. Because again, we're talking vertical up and down. So it's applying on the outside. We have our f of x plus k. Now, I haven't been doing it, but if you like writing out the g of x on each line, that's perfectly fine. Like on the first one's writing g of x or h of x all the way down, that is perfectly fine. If you're able to keep it straight, the g of x is going to be applied to every single side of that equal sign. You only need to put it at the first and last. Okay. So we're moving it 5 units. So this would be, we would have a 5 and our sign would be positive. Up is positive. Down is negative. So what is our function f of x? Minus 9. And it's still f of x. That didn't change. We didn't change anything inside. So we can plug in 4x minus 9 plus 5. Well, nothing to apply or distribute through those parentheses, so we can drop them. 4x minus 9 plus 5. Combine like terms. 4x minus any questions on any of this here? Do you feel comfortable with this here? Yes? All right. If there's no question on this here, we've got it written down, yes, because I'm going to have to erase it to get at the other one. Where's my sign? Again, I'm just rewriting it so I can remember it. Our other one, write a function h whose graph is a translation 1 unit to the right of the graph of x. Well, for us here, it's going to be f of x minus h. Oh, I wanted to put k. I did that first hour too. So what is our value of h? 1, and it would be positive. The value that we plug in is positive, but what we end up is with x minus 1. because the value of h is positive, but because of how the function and how this works, it looks negative now. We're moving on. So this here, we're now replacing x with what? X minus 1, yes? So every place that there's an x over here, we're going to replace it with x minus 1. So we have 4 times x minus 1 minus 9. Then what would we need to do next? Distribute the 4. So we'd have 4 times x, which is 4x. 4 times negative 1 is minus 9. And when we combine our like terms, the negative 4 and negative 9, we get negative. And that there is our new function. Any questions on this here? We ready for the next one? These here are actually even easier than the ones we just did, interestingly enough. So the first one here, f of x equals 3x, and we want it to have a translation of 5 units. Oh, does anybody have a guess at what the function would be? Well, let's see how that works. Because the way we would set it up is f of x plus k. Since we're moving up, it would be a positive 5. And f of x is what? Because the original function didn't have anything added to it, it's just 3x. The 5 almost is just added on to the end. Any questions on number 1? Number 2, we want to translate this function 4 units to the right. You have a guess? Yeah. Because again, we're doing f of x minus h, which would be our f of x minus 4, and it'd be minus 4 since we're moving to the right. Positive 4, but when it's inside the parentheses, it looks negative. And again, just like we did before, since we don't have f of x anymore, we have f of x minus 4. We're replacing this x and every x inside the function with x minus 4. Now, I would normally put parentheses around it just in case there's anything inside there. Because if it was 2x, it's a good habit to get into. But since there's nothing inside the absolute values, we can just say the absolute value of x minus 4 minus 3. And that is it. Any questions on this here? All right, the next thing we're going to look at is reflections. Reflection in the x-axis and a reflection in the y-axis. Now, the reflections in the x and y axis are actually pretty straightforward. At least I think so. If they're not for you, that's not bad. There's nothing wrong with it. I've been doing it a while. With the reflections in the x-axis, let me just get the highlighter out again. We're going to be dealing with y equals negative f of x. So we're going to be applying the negative to the outside of the function, or applying it to the function itself. Whereas the reflection in the y-axis, we're going to do y equals f of negative x. We're applying it to the x. So the reflection in the x-axis, across the x-axis, is taking it and flipping it across that line. A reflection in the y-axis is reflecting it across the line y equals 0. So equals negative f of x is the x-axis. Y equals f of negative x is the y-axis. Now, when I talked about these yesterday, kind of reflections, I talked about a little bit with inputs, outputs, affecting the input, affecting the output. When we talked about moving stuff up and down, we're talking about the output. We're changing the output and moving it up or moving it down. With reflections, again, with the x-axis, when we're reflecting across the x-axis, we're changing the output from positive to negative or negative to positive. And that's easier to see in this form because here, negative f of x, whatever the value for f of x is, we're changing it from positive to negative. F of x is our y, what comes out of the function. So making it negative is we're flipping it. We're changing it from positive to negative or negative to positive. Changing the output. Here we're changing the input. Negative x, we're changing what goes in because if I would have normally plugged in a positive number, well, now it's negative because the negative x. If it was originally negative, well, negative and negative make a, so now it's positive. So it's changing the input. Across the y is changing the input. Across the x is changing the output. And these here you'll like a little bit more than even the horizontal and vertical. So let's look at this first function here. Write a function g whose graph is a reflection in the x-axis of the graph of f. So our g of x. So he said x-axis, if we're doing that, would be negative f of x. Would be negative f of x. Well, now we just need to replace f of x. What f of x is this whole thing here. So the absolute value of x plus 3 plus 1. In this one here, we do need the absolute, or the parentheses around the whole thing, because we have a negative being applied to the entire function. So for this here, we're going to distribute the negative to both parts to be able to simplify this down. Now, when we multiply the negative by the absolute values, it stays on the outside. We have negative absolute value of x plus 3. And negative times 1 is going to be negative 1. And that's it. Any questions on this here? We kind of like this. Essentially, what did we do? We changed the signs in front of each one, made them negative. This again is for my own sake. write a function h whose graph is a reflection in the y-axis of the graph of f. Now for us, the y-axis is going to be f of negative x. For across the y-axis, it's f of negative x. We're changing the input from positive to negative. Which means since I don't have f of x anymore, I have I have to change every x in the function from x to negative x. So inside the absolute value bars, we would have negative x in parentheses plus 3 plus 1. Now, since there's nothing being multiplied by x that we need to resolve, we can just drop the parentheses and have negative x plus 3 plus 1. That's it. Any questions on any of this here so far? All right. Let f of x be the absolute value of x minus 5 minus 4. Write a function h whose graph is a reflection in the x-axis of the graph of f. So x-axis, we would have what? Negative f of x. Negative parentheses. Well, we can go on and put what f of x is. The absolute value of x minus 5 minus 4. What do we need to do next? Clear out the parentheses by distributing the negative. Now, the negative does not go into the absolute values. It won't just go inside. It stays on the outside. So that becomes negative absolute value of x minus 5 plus 4. The negative 4, a negative and negative would make a positive. More or less what we're doing is we're multiplying everything in the function by negative 1. So negative 1 times the absolute value would be negative of the absolute value. Negative 1 times negative 4 would make it positive 4. Any questions on this here? Write a function g whose graph is a reflection in the y-axis of the graph of the function f. So which one would we be using this time? Exactly, f of negative x. Which again, just like with the last one, we're going to replace every x with a negative x in the function f of x. So that means we'd have absolute values. Negative x minus 5 minus 4. We can drop the parentheses. And have our function. And that's it. Questions on this here? Do we need to see another example of one of these? We feel comfortable with this? With reflections? Yes. Trenton, we good? Do you want to see one more? Okay. There's nothing wrong with seeing one more. So with this here, we want a reflection in the x-axis. Yes, so which one are we going to use? Well, negative f of x, because that's our one for the x-axis. So we're applying a negative to the outside. So for us here, we're going to be applying a negative to f of x, this entire function. So we'd have negative absolute value of x plus 2 minus 1. Now, essentially what we're doing is we're multiplying every part of this function by negative 1. So a negative times a negative would be a, so a positive absolute value of x plus 2. Negative 1 times negative 1 would be plus 1. So this here would be our new function. Any questions on this here? We good with this one here? Okay. All right, let's just look at one last one. This one here is a reflection in the y-axis. So this one here would be f of negative x, which means we're going to be replacing the x with negative x in the function. So instead of having 1/2 x plus 1, we have 1/2 times negative x plus 1. And last but not least, to simplify this here, we're going to do 1/2 times negative x, which would be negative 1/2 x plus 1. Now this here is the last type of transformation we're going to look at, is stretch and shrink. Now we don't focus, I personally don't focus too much on horizontal stretch and shrink because it is a little bit confusing on how it works. The graph of y equals f times a of x is a horizontal stretch or shrink by a factor of 1 over a. So whatever they say the stretch or shrink is, we have to put it as 1 over a. We have to take its reciprocal. So if they said the horizontal stretch or shrink was 4, a is equal to 4, what we actually apply into the function is not 4, it is actually 1 over 4. Or if it says that the stretch or shrink is 1/4, what we put into the function is not 1/4, we actually put in 4. Clear as mud yet? Now, multiplying the input by a before evaluating the function stretches the graph horizontally away from the y-axis when a is between 0 and 1. So if the value they give us is between 0 and 1, then it's a stretch. And shrinks the graph horizontally towards the y-axis when a is greater than 1. So we're talking horizontally. If the value of a is greater than 1, then it is a shrink. If it's between 0 and 1, it is a stretch. But before we can input it into the function, we have to flip it. That's too much. That's why I don't cover this, because there is so much going on in here to try to unpack. I think it's possible that y'all can do this, but I feel like this is such an easy thing to get flipped and try to keep track of. I don't mess with it. Because when we look at a function, even if they told us that it's what f of x is equal to 2 times 3x squared. The 3x inside, the 3 would be our horizontal stretch or shrink, but it wouldn't be denoting it with the 3. It would actually be what? It would be 1 over 3. We have to have the 1 over a. So that means it's a horizontal shrink or stretch because it's between 0 and 1. It's not by a factor of 3, it's a factor of 1/3. So it's one more thing to try to keep track of in all the stuff that we're doing in this chapter anyways. I don't mess with it. We don't mess with this part here. Now, vertical stretch and shrink we will work with, because the graph y equals a times x f of x is a vertical stretch or shrink, where a is greater than 0 and a is different from 1. Why would we not consider the case when a is 1? Well, what's 1 times anything? Just whatever the other thing is, yeah. Because 1 times 2 is 2. When we multiply by 1, it's not changing the function. It's not doing anything. We just get back the original function. So to not even put that case in here to begin with, they remove it in both of them. Multiplying the output by a stretch stretches the graph vertically away from the x when a is greater than 1, and it shrinks it between 1 and 0. We can kind of get that. Fraction, so between 0 and 1, those numbers would obviously make it smaller. If it's greater than 1, it's going to make it bigger. We can see that. We get that. And that makes a little more sense. Well,